Welcome everybody to day 2 of the notes. Again, this is Mr. Ratoon. And if you're in Mr. Phillips' class, this may be your day 1 notes. Again, like I explained in the last set of videos, if you've watched it, we actually flip our notes around a little bit, which allows us to do some different labs at some different times because we share a lot of the same equipment. So it's not prudent for us to be on the same set of notes at the same time because we can't do the same lab at the same time because we don't have enough equipment. So today we're going to be taking a look at the Earth, what's in the Earth, and how it may help us later on with plate tectonics and explaining plate tectonics. Now, the liquid origin of the Earth allows for one really important thing. It allows for the density layering. So what I mean by the liquid origin of the Earth, a lot of scientists theorize when the Earth was created that it was once molten at one point in time. And if you've ever had anything that's molten, if you think of Jello, Jello is a pretty good example of this. When you first make Jello, you can actually drop fruit into it, and you may have had this at a dinner party or a family reunion or something. But you can drop fruit into it, and as the Jello starts to solidify, you can drop different fruits into it, and the fruit will actually layer at different points in the Jello. And the Earth was similar to that, where when it was first created and was liquid, all the densest material drop to the center of the Earth. And you'll see that comes into play later on in our notes. So the liquid origin of the Earth did allow for density layering of the Earth because the densest material is located in the center. And there's 3 main layers of the Earth. There's the crust, the mantle, and the core. Sometimes you'll see here at the bottom where we see the core and the inner core. Some people actually divide this into 4, and they'll say the outer core is your 3rd and the inner core is your 4th layer of the Earth. So we're just going to use 3, but some scientists, some books, some articles will talk about 4 layers of the Earth, and that's what they're really talking about. Now, one of the questions that often gets asked is, how do we know about the inner Earth? And people will say, ask a common question is, have we ever been able to drill through the crust? Have we gotten into the mantle? Have we gotten into the outer core like some of the movies talk about? And the answer is no. About the farthest we've ever been able to drill into the Earth, and when I say we as humans, is a little over 12 kilometers, about 12.2 kilometers. And this was in the Kola Peninsula, and it was done by the former Soviet Union, the USSR. And they weren't very successful. You might say 12.4, that's quite a ways. But yet, when you look at the crust, average is about 35 kilometers thick. So 12.4 is not that far down into the crust. More recently, we've been able to drill down 1.4 kilometers into the crust. You might say, well, golly, that's not very far compared to 12.2. But with that, we actually drilled underneath the ocean. You see, the crust on the continents is a lot thicker. If you go to the bottom of the ocean, the crust is a lot thinner. So when they recently drilled down about 1.4 kilometers, they actually got within about 1,000 feet of the mantle. The problem is once you get down too far, the heat's going to be a problem. The pressure is tremendous. A lot of times the pressure is so great it'll crush the metal casing that you have around that lines the drill casing. So you got to overcome this pressure. You got to overcome this heat. If you drill in the bottom of the ocean, the pressure is the same problem. How do you get your drilling equipment down to the bottom of the ocean? So a lot of people ask, how do we know? How do we know the middle of the Earth isn't just made out of, say, marshmallow fluff? Well, there's certain pieces of evidence that we use. And one of these, you can see right here, is labeled earthquakes. And you might say, well, what does this have to do with anything? Well, when an earthquake happens, you can see that seismic waves travel through the Earth. And when they travel through the Earth, they actually travel at different speeds. And the speeds will depend on several things. So it'll depend on the density of the material. It'll depend on the temperature of the material. And you can also see in certain locations, such as right here, when it hits certain layers of the Earth where there's a huge density difference, it'll actually change direction. Oops, sorry about that. There we go, let's get rid of that. But you can see how it changes directions. So scientists have been able to study the layers of the Earth. They know the approximate thickness of the Earth. And now this looks like it's perfectly lined, but it's not always that perfect. And what scientists have figured out is through these density layerings, through the earthquakes, and they've been able to find a different sections where one layer starts, the next layer begins, where the temperatures change. And they've been able to get a pretty good idea of the density of the Earth based on the speed of these earthquakes that have traveled through the Earth. So this is one of the main ways that they've been able to figure out where the different layers are. Another common thing that they'll use is magma or lava that's come to the surface of the Earth. And they can analyze what's underneath the crust by taking a look at this magma. And they can look at the chemistry of at least the mantle. So let's start looking at the layers of the Earth. You got the crust. The crust is the least dense of all the layers. The crust is mainly composed of elements such as silicon, oxygen, and aluminum. And you got all kinds of elements in there, but these are the main ones that are in there. And when you look at it, silicon, oxygen, aluminum, they're all pretty, they're less dense minerals. They're not the heavy minerals that you're going to find, which makes sense because if we have a density layering of the Earth, the least dense layer should be the crust on the top. Now, the average thickness of the Earth, or of the crust anyway, is 3 to 20 miles thick. Now, you might say, well, only 3 miles thick? That's not very far. Problem is that 3-mile thickness is on the bottom of the ocean. But the crust itself can be up to 20 miles thick, and it tends to be thickest on the top of the mountains. So if you go to top of Mount Everest, it's really tall mountain. Plus, if you think about it, if I draw a picture of what the Earth would look like, and if you have Mount Everest right here, well, what's going to be underneath? If this is your crust, you've got that huge mountain that actually is going to come down because it's got to be able to support all that weight. So it tends to be the thickest over these mountains. And when we look at it here, it'll actually be the thinnest, if we're going around here, it'll be the thinnest under the oceans. Problem is drilling underneath the oceans. Now, are we ever going to be able to drill into the mantle? Yes. Technology keeps improving. Eventually, we're going to be able to get down into the mantle. It's just a matter of time and a matter of money, because it's going to cost money to be able to do that. Now, the crust accounts for only about 0.4% of the Earth's total mass and less than 1% of its volume. So you look around you, the Earth is huge. You look at the crust, wow, it's large. You look at these mountain chains, they're large. But it's actually a very, very small percentage of the Earth's total mass and total volume. Now, the ocean crust is primarily basalt, and the continental crust is primarily granite. Keep in mind these two facts. These two facts are going to be huge later on in our notes. And we actually talked about these. Remember when we talked about these during our rock units, we talked about basalt being more dense, darker, heavier rocks than your granite. And that would be a key fact later on when we talk about plate tectonics. Now, the mantle, the next layer of the Earth. The mantle contains things like silicon, oxygen, but it has more iron, magnesium, and calcium than the crust. So when we start looking at minerals such as iron, magnesium, you can know that it's going to be more dense than the crust. And the mantle is approximately 1,800 miles thick. So when you looked at the crust, you were looking at 3 to 20 miles thick. Now you're looking at 1,800 miles thick. So the mantle is quite large. The mantle is separated from the core and the crust by two parts. You got your Gutenberg discontinuity, and the discontinuity basically, if you break up the word, you got your continue right here, and your dis means something is discontinued. It means they've broken it up. It's no longer continuous. They don't sell it anymore. So if something's discontinued at a store, they don't sell anymore. So discontinue means the layer of the Earth has been broken up. It's divided. And you've got two of these discontinuities. You got the Gutenberg discontinuity and the Mohorovic discontinuity. And this was named after a gentleman in Russia who basically found it by looking at seismic data. And this separates the bottom of the mantle and the core, and this separates the top of the mantle and the crust. So when we look at it, you've got your core down here, and there's a distinct layer. So if you had an earth wave, a seismic wave coming through here, it'll bounce off that, or it'll reflect off that. Sometimes it'll bounce off it. So scientists were able to analyze these waves to figure out that you have the Gutenberg, and it's kind of hard to see right here. Looks like it's at the surface, but you actually have the crust right above it. So scientists were able to find out, let's just call it the MOHO discontinuity for short, and that separates the crust from the mantle. Now, the Earth's mantle makes up about 68.1% of the Earth's mass and about 83% of its volume. So you can see that this is a much, much more massive part of the Earth than the crust. The average density of the mantle is approximately 4.5 grams per cubic centimeter. So it's dense, but you're going to see that's going to get even denser as we go down. Now the core, you got the inner core. The inner core is very dense, and it's made up of solid nickel and iron. It's about 800 miles thick. The outer core is quite dense. It's still gonna be dense, but not as dense as the inner core. And it's made up of liquid nickel and iron. So you can see that the big difference here is this is made up of nickel and iron, but it's liquid. This is made up of nickel and iron, but it's solid. And the big question is why? Why is this solid? As you go down inside the Earth, it should be getting hotter and hotter and hotter. And if it's getting hotter as we go down, shouldn't this nickel and iron be molten? If anything, shouldn't this be switched around? Well, what do you think causes this to be solid? We're actually going to do a lab on it. It's the Oobleck lab, where we're going to take a look and see what happens when we apply a lot of the big P word to the Oobleck. And the big P word is going to be pressure. When you look at the middle of the Earth, there is a lot of pressure. So, I mean, if this is the core, you're going to have pressure from all around the Earth. Everything's going to be pushing down. And even though it's getting hotter and hotter, what scientists theorize is that there's so much pressure in the middle part of the Earth that even though it's hot, it's going to be a solid because of the extreme pressure that's being exerted. Now, the core as a whole makes up about 31.5% of the Earth's mass and about 16% of its volume. And look at this. Now the density went from 4.5, or approximately 4.5 in the mantle, to 13 grams per cubic centimeter. It's very dense as you get down towards the center of the Earth. Now, the inner core is thought to be solid due to the extreme pressure it is under. So we talked about that a few slides earlier, but that's all right. Now you got it twice. And as the Earth rotates, the liquid outer core spins around the solid inner core, creating the Earth's magnetic field. That's one of those interesting things. So when you have the Earth, so if I was to draw the Earth here, you know, you have the mantle, and then here's your inner core, and then you got, or your outer core and your inner core. And it's kind of interesting. As the Earth rotates, so does the outer core. And what's interesting about it, the outer core actually spins just a little bit faster than the Earth. And what it does is actually creates a magnetic field. And on other planets that we have in our solar system, you've got the inner core, but it's not spinning. It's basically frozen solid. It's not liquid anymore. And as a result, they don't have a magnetic field. And what we've found out is that this magnetic field, yes, you know, gives us polar north. So if you're, you know, that's why your compass always points to the North Pole or close to it. It's not due north. It's actually a little, they call it magnetic north. But this also helps us shield us from radiation that comes from the Earth's sun. That's why we get things like the northern lights, because it's the sun's radiation going through the magnetic field of the Earth. And as a result, we're actually protected from a lot of those rays where a lot of other planets aren't. So here we see some different drawings of the Earth. Here, this is kind of neat. You know, people always ask, how hot does it get? And this is in Celsius, so it's kind of nice to look at both. Where, you know, it starts out at 0 degrees Celsius, and this is basically where we are up here. But as you go down, you know, it gets to be 7,200 degrees Celsius. And you got to remember, 100 degrees Celsius equals 212 degrees Fahrenheit. So you know if this is 7,200 degrees Celsius, what would it be in Fahrenheit? It would be a lot hotter. A lot hotter. And that's why, you know, even if you go down into, you know, this area down here, and if you do go not too far down into the Earth, some of the deepest mines in on Earth, they actually have to air condition the mines because it gets hotter and hotter. So if you go down to a cave, like if you've ever been to the Cave of Mountains, yeah, it's going to get hot, but not nearly as hot as if you keep going down further and further and further. Now, Here's another picture. You can look at the different layers of the Earth. But let's talk about one more thing. Let's talk about some sublayers. Above the outer core is the lower part of the mantle. And we know that this lower part of the mantle is rigid and it's not really deformable. And it actually resides on top of the, or actually it's below the middle part of the mantle. So the lower part of the mantle tends to be more rigid, not deformable. But right above this layer, the middle part of the mantle, we call this the asthenosphere or the asthenosphere. And this asthenosphere is actually hot, slowly flowing plastic-like layer. If you think of the word plastic-like, people say, well, what do you mean plastic-like? Well, think of a piece of Tupperware. I can take a piece of Tupperware, I can bend it, I can move it around, it's flexible. Well, that's kind of like the asthenosphere. It's a solid, but yet it flows. It's plastic-like. It's thick. So, I mean, it's not going to run like a liquid where it's going to pour out really fast, but it's going to be slow-moving layer of the Earth. And the lithosphere actually resides on top of it. The lithosphere is a cool, rigid, thin upper layer of the Earth. And what happens is that this lithosphere doesn't just include the crust. It actually includes all the crust, both oceanic and continental, as well as the very, very top part of the mantle. And this lithosphere actually rides on top of the asthenosphere. So we're starting to build plate tectonics here. Because remember, this is the crust. This is what Wagner said moved. That he said this crust plowed through the ocean floor. Now we're starting to see that there's this thing called the lithosphere. And you're going to be later on, you're going to realize that it's also called a plate. These are, when we talk about plate tectonics, we're talking about lithospheric plates. And we're going to learn that these plates actually ride on top of this slow flow moving asthenosphere. And this is what's going to allow these plates to move. And we're going to get into that more in our next video. So here we see the lithosphere. The lithosphere is going to have different thicknesses. Again, like I said earlier, over the top of these huge mountains, this is where it's going to be the thickest. But if you go to the bottom of the oceans, here the lithosphere is going to be the smallest. And what moves these lithospheric plates? What causes them to move? And scientists believe that there's convection currents deep inside the Earth. And these convection currents are created due to the heat generated from the Earth's interior. Remember, as we go deeper and deeper inside the Earth, it gets hotter and hotter and hotter. And as things heat up, they become less dense. If you've ever been, I don't know how to describe this. Say if you go to the stove, let's say if your mom's cooking, you can put your hand, 2-3 feet above the oven or above the burner on your cooking stove, on your stovetop, and you can feel the warm air rise, and that's because warm air is less dense, so it rises. Well, as the lithosphere heats up, remember, it's liquid-like, it also rises and it creates these currents. And when these currents cool off, they become more dense and they sink. So if you can imagine, deep inside the Earth, it's going to be really hot. And as it heats up, it's like a stove. It's heating up this asthenosphere and this plastic-like layer, and it rises up. Now, it can't just drop straight down because there's more of it coming up and more of it coming up. What scientists theorize is that this comes up, and as it starts to cool down, it drops back down. And it creates these currents. And as these currents move, they move the plates. Now, are these plates moving hundreds of miles an hour? No. They may only move a few meters a year. And that's why our plates don't move very fast. And this is going to be the basis of plate tectonics and how things move. Now, there's other theories out there, and this is kind of addressing the slab pull theory. And if you want to learn more about that, it's in your readings a little bit. But it basically says as this rises up, that the slab starts to pull off, and it starts to pull it. And it might actually be pulling it. Once it starts getting pulled down inside the Earth, it just keeps pulling it and pulling it, pulling it. So sometimes we'll talk about it being a ridge push slab pull theory. And they might both work together to cause these plates to move. And we're actually going to do a lab where we're going to take a look at these convection currents. And the lab that we're going to do involves a Bunsen burner and heating up, and it's going to involve some oatmeal. So you don't want to miss that lab that we have in class. So do scientists know exactly how these convection currents work? No. Again, they just have some theories. And you can see some of the different theories. Some people believe the core is heating them up. Some people believe that these convection currents aren't nearly that deep. And hopefully one day we'll be able to drill down into the earth and we'll be able to explore it and we'll be able to find out for sure. Well, that doesn't conclude day 2 notes. So as always, if you have any questions, just ask.